Greetings. Welcome to DAU's AI video learning series. This video will explore applying DoD's ethical principles to machine learning use cases. This video will build on material from two prior videos in this series, AI ethical principles and responsible AI, and insights into a simple neural network. You may want to watch these first, and if so, you can click on the thumbnails, and those will take you to those videos, or if the link in the video doesn't work, the link will be also below in the comments. So in the AI ethical principles and responsible AI, we discussed the 5 DoD AI ethical principles and how these principles emphasize that DoD's AI systems should work. We talked about the responsible principle. People would be held responsible still, and the system should be used wisely. We talked about the equitable principle, that they should treat everyone fairly. We talked about traceable. The system should be transparent and understandable. And we talked about reliability, that they should work reliable and as expected. When the warfighter turns to them and pulls the trigger, they should act as they expect them to act. And we talked about governable, that the warfighter should always remain in charge. These systems should always remain under human control. Okay, and then we also talked about in the insights into a simple neural network, we talked about using a simple feed-forward neural network to control the steering of a simulated vehicle that we drove around a track. And in that example, we used a simple little sensor in the front of the car to provide 8 inputs that sensed the road in front, and provided those inputs to a feed-forward 4-layer network that provided an output steering command. We also talked about how once we got the neural network built and we got the environment simulated, we had to curate a data set. We had to collect a data set and fabricate a data set on which to train this network. And we had to take our vehicle out with its sensor and put it in various positions on the track in the environment that we expected it to be in, and take snapshots with that sensor. And for every look at the sensor we thought the sensor would see, we had to have a corresponding piece of data that was the output that we would like the network to say. So in this case, we'd take a snapshot of the road and we would have a piece of truth data that said turn right. In this case, we'd take a snapshot of the road, we'd have a piece of truth data that said make a slight left turn. Here we'd take truth data, say make a slightly greater left turn, and here we might have a piece of truth data that associated with that sensor input that said continue straight. And then once we had all that data, we went ahead and trained the network, and we would put each one of those data points with its those sample data points with its truth data associated with it into the network. We'd first randomize the weights. We'd put that we put it in training mode, so we were training the network. We'd put each piece of data in, and we'd see what the output was from that data set. We'd compare that output to what we wished that, or the truth data, what we wanted the system to produce. We'd get an error function, and using a back propagation algorithm, we would adjust all the parameters between the connections between the neurons. We thought of it as adjusting knobs, kind of tuning the network or teaching the network, if you would. And the back propagation algorithm would back propagate and adjust all the knobs. And it would do this for every single data point in the training set. And usually for multiple times, you'd run through the same training set multiple times or multiple epochs. This was called supervised training, and we would continue that supervised training until the error function got down to an acceptable value or near 0. And then after we finished training it, we took it out on our track. We had various different tracks, and it usually worked really good on the track. It stayed right down the middle of the track and worked well. And we had different kinds of tracks, ovals and figure eights, and it always worked well until we put it on a track where it didn't look like the training environment. So this track, you'll notice, has got yellow edges, where the last track had no stripes along the edges. It just had dirt on the outside. This one was elevated, had yellow edges. And so it didn't look like the training data, and hence we didn't get results that we expected because we didn't use a good training set that was representative of the use cases. So clearly in this example, tying this back to the ethical principles, we can jump right on down to the 4th one, reliable, and say, hey, this isn't reliable. But before we get there, let's back up and let's go through these one-on-one. All right, well, so we're talking about the responsible principle. And in that responsible principle, that means the people in charge are still responsible. Okay, so if me and you were creating this system for the warfighter and we handed that over and we didn't use a representative data set, we would still be responsible for the development of that. If the warfighter knew that data set that it was trained on didn't look like the use case that it was getting ready or she was getting ready to use it in, and went ahead and used it anyway, she would be held responsible for that. So the people are still held responsible. We're not just going to blame it on the AI. Equitable, this was more to do with systems that dealt with people to make sure that people were treated fairly. But you could say, in a way, I mean, because the system's going to perform like the data on which it was trained with. So if the data it's trained with has a bias, then the system's going to reflect a similar bias. So in this case, you could say that little simple neural network was biased to work on tracks without yellow stripes. And in some way, that's another perspective you could look at here. Okay, so the traceable principle, on traceable, we're saying that the people involved understand the system, understand the technology, understand the development processes, understand the operational methods and how it works. And in this case, you could say, is this the right system for the right job? Yeah, yes. Is it what kind of data was it set on? So basically, the people are still responsible. So this is kind of the other half of this responsible principle. It has to be traceable. You have to understand the data sets that it was trained on, understand the limitations of the system and how it works, and the people involved need to understand all that. But then there's a second aspect, if you will, to the traceability, and that's the system itself. It has to have a certain degree of auditability and a certain degree of transparency, so where we understand why the system made the decisions it made. Now, these are going to be different for different systems. The requirements will be different, but you certainly want to understand or have as much understanding as you can on why the system acted like it did. And so for our case, we have a very simple little network here, but still, even in this very simple network, this isn't traditional computer logic. I used to work with aircraft, and when we had Class A mishaps or accidents, we'd have investigation boards, and we'd have to get down to root cause. And oftentimes, you're tracing through software that's in the line replaceable units in the boxes on the airplanes, and you're trying to figure out if the software took a logic branch it shouldn't have, and why it took that logic branch, trying to get down to root cause to why the system failed. Well, there's not really traditional logic here. There's no if, then, else statements. If this happens, then do this, else do something else. It's really hard to say. The information is really buried in all these different knob settings and conditions. And while we can appreciate it with a simple neural network, if we get, today's networks are certainly going to be much more complicated than that. If we took a network for to drive a real car, to operate a real car, it would certainly be more complicated. This is just a little cut and paste to give you a feel for a much more complicated system. While the system we talked about was certainly applicable to today, we'd have many more neurons, many more layers, possibly various different architectures involved besides feed-forward networks or even other than feed-forward networks, and different training algorithms. But nevertheless, what we talked about would apply. And but to drive a real car, of course, you're going to have a much more complicated sensor, and there's going to be a lot more involved than just steering like what we did when we were doing our little example. But nevertheless, let's say this network is representative of the neural network, if you will, that drives a real self-driving car. And let's say that we trained it with a vast data set, and it had sensors that looked out in the front, visual sensors, and we saw a stop sign. Okay, and we trained it with 10,000, many thousands of data points, and every time it saw the stop sign, we got the correct output out of it that said apply brakes. And so we felt pretty good that this thing was working pretty well. But then one day we tested it, and lo and behold, it didn't say apply brakes. It said actually accelerate. And we were trying to figure out, well, what the heck's going on with that? Why did it say accelerate? Is it traceable? Is it audible? Why? Where is that? Where is that information? How can I trace that logic and figure out why all of a sudden a stop sign said to accelerate instead of not? So that kind of takes us to that traceable principle and the traceability part of that. If we kind of try to figure out why the network said what it did, it's buried. The information is buried in these thousands and thousands, and sometimes hundreds of thousands, and even billions. If I heard a Caltech professor the other day say the ChatGPT had about 180 billion parameters. So that would be 180 billion knob conditions. And, there's no stop sign location in here. There's only parameter weights, and the networking of all these parameter weights is what takes this scene and turns it into an output. And it's always going to give you an output. You put an input in, it's going to propagate through, and it's going to give you an output no matter what. So, now why did it give you that output? Well, was it this knob was set this way, that knob was set that way, this knob was set a little bit wrong that way? It's very hard to trace it that way, because it's all in those stop weights. Oftentimes, though, if you look into this, you'll see that the data involved in the training may have something to do with it. And so if we trained it on a data set that wasn't representative of the environment, we could get unexpected results, just like we saw with our little car. Well, if you look really closely at this one, you'll see, hey, somebody stuck a sticker on the stop sign here that we weren't expecting. And while to us, to the human, this is obviously still a stop sign, and we maybe didn't even notice this little sticker, that little bitty sticker could produce a completely different result. And so the auditability and the traceability sometimes are in question, but a lot of times it does come down to the data set. And it would be nice to know if there was maybe a wrapper software that went around it, or maybe another AI watching this AI that could compare and say what the confidence was that the data that it's seeing now in the real world was representative of the training data set, and maybe give the warfighter some kind of a confidence thing. But the services are working through that and seeing how we're, what traceability really means, and how we can use this, and when we can learn to trust the system, and when we can know that this system needs to be switched off because it's not being used in a situation that was representative of what it was designed to work with. Okay, so that's the traceable principle, and now of course we get to reliable. And when the warfighter turns to this system, they need it to work like it's supposed to work. They need to know that, hey, when I pull the trigger, it's going to do what we expect it to do, and it certainly needs to be reliable. And that one's pretty easy to understand. Often it comes down to the right system, the right use cases, the right training, and understanding how that works. Now that brings us to the governable principle. If in fact, in the example we just had, you've got a training data set in the real world or you've got a set in the real world, an environment in the real world that's not representative of the training set, so you the warfighter maybe know the confidence is going to be low. Wouldn't it be nice if the system had a way to tell you the confidence was going to be low, or you just knew the confidence was going to be low? You have to be able to switch off the system, and that's the governable part. The humans need to remain in control. We need to be able to take alternate means, turn off the system, and continue on in such a manner. Okay, so that was the the 5 ethical principles. Those are part of the DoD's responsible AI strategy, and you can find the link to that here if you'd like to read more about that. Any of DAU's AI courses, you can go ahead and click here, and it should take you to a curated playlist of DAU recommended courses that we recommend. If for whatever reason that doesn't work, you find the link in the comments. And again, thanks for watching, and please check out the other videos in this series. And again, like and subscribe if this helped you. Thank you very much.